Hello kidlets, this is going to be your first notes video for our next unit on the moon. So here is the basic outline, and this video is going to cover the first two sections on lunar surface features and the formation of the moon. These are our different sections, moon phases, eclipses, and also impact cratering. So just a couple things to note for these and all following notes. Whenever you see these two little asterisks here, that implies something that is for a deeper understanding. So for example, when I talk about impacts and the energy difference, if all you care about is that one impact has a higher energy than the other, fine. But if you want to know how those numbers are derived, it would be here. So this would be more technical, deeper understanding if you really care about the how instead of just the what. So otherwise, just ignore those. So the first section we are going to be covering has to do with lunar formation and how we got the moon in the first place. There have been a few different ideas as to how that is. Darwin's son, George Darwin, he came up with this idea of fission, of splitting atoms and splitting two particles. So he thought that maybe part of the Earth split off and that became the moon. The idea of co-formation, that when the solar system was coalescing and all of the different planetary bodies were accreting, that these two bodies just formed out of a bunch of different solar system debris and became to orbit one another, moon orbiting the Earth because it was smaller. Capture, and we see capture in terms of larger planets, even in terms of Mars, which is only a third of the size of the Earth, but has captured at least one of the two small asteroids. The other we don't think is actually from capture, but planets that are more massive, such as Jupiter and Saturn, have captured dozens of moons. And then the last is the impact. And again, we see evidence of impacts everywhere we look in the solar system. So we know that the early solar system was a really busy place. There was tons of impacts going on. In the early solar system, we had our early sun, and for the first 3 billion years of Earth's history, the sun was not quite to the brightness that it was now. In fact, the sky would have actually been only about a reddish orange for 3 billion years. So we've only had a blue sky for the last 1.5 billion years of Earth's history. So we had a bunch of different debris and dust. All of those dust particles accreted together, much like forming a snowball. And that became the planets, the asteroids, the comets. And things settled based on their density and the temperature regions of the solar system. So what we now know to be the accepted model of lunar formation has to do with the impact theory. And this was that a Mars-sized object collided with Earth early on in solar system history. It collided after the Earth had already differentiated. We'd already formed a core. It was a glancing blow, an oblique, low-angle blow, not a direct blow. It formed a debris disk. That debris disk came to orbit around the Earth and then came to coalesce into a sphere and orbited around us. So sometimes this is called the Theia hypothesis because the impactor is commonly known as Theia. There have been many different computer-generated models, and in this computer-generated model you can see, we're going to go to our pointer for now. You can see the areas of differentiation. The blue would be the core and the lower density material moving away. So that represents the separation by density or differentiation, which all planetary bodies go through. And it's important to note that Earth had already formed a dense core when this happened, because that allowed Earth to still be stable and remain after this impact instead of just disintegrating. And then quickly, within days, no later than 100 years, that debris disk would have formed the moon. So here we can see the moon in a lunar eclipse. So when it scatters the red wavelengths of light when it comes into Earth's shadow. There's a link here for a movie. Please feel free to watch. So here we can see a pretty good play-by-play of what that would have looked like. So this would have been about 200 million years into Earth's history, so very early on in solar system history when we had lots of large impacts, lots of activity in the inner solar system. So here we can see that glancing blow, and this would have been after Earth had already formed a core, which is important because since there would have been lower density material at the surface, this impact being a glancing blow would have shock heated the entire surface, creating this idea of a magma ocean. So it would have superheated the entire surface, turning it to a liquid, vaporizing all of the material at the surface, So then when this impact happened, the original impactor sank to the core and became Earth's core. And what remained, this debris disk that formed, was due to the inmixing of the original material and the shock heating of Earth's surface. So essentially the moon was formed from this shock heated, melted debris from Earth's crust. So it was completely inmixed and reshaped and quickly formed the debris disk, which then that material accreted to form the moon. So there would have been a large angular momentum within the Earth-Moon system, which then contributed to Earth's rotation, and we can see similarities in the tilt of Earth and the orientation of Earth's moon, which further supports this idea. And astronomers noticed before the Apollo missions that the spectral signatures of the moon and of Earth's rock looked very similar, but we didn't have that tangible proof until the sample return missions of Apollo. So this is what planetary differentiation would look like. So an undifferentiated planet early on in its history would be very homogeneous. You would have low density and high density particles existing throughout the body, and once it is differentiated, you would have the higher density material which would sink, the lower density material would be at the surface, and in planetary science we know this is a core, a mantle, and a crust. And all bodies would have this, even asteroids do. But one thing that is interesting to note is that asteroids have survived so many collisions that most of them are all orbiting cores. These layers have all been blown away because they've been through so many impacts. And the core is generally this very dense iron. So most of the meteorites that we have on Earth are fragments of these iron cores of these asteroids that are between Mars and Jupiter. So we'll talk about this later on when we talk about impacts, but when people have this whole Hollywood idea of just blowing them up if they come close to us, well, you can't really do that if you have one iron piece that's coming towards you. That would then make thousands of iron pieces. That doesn't make your scenario any better. So here he just talks about the compositions, and again, that would be for deeper understanding if you were very interested in geology. And then again, that core of Earth would have been comprised of the highest density material from that impactor. So originally, this theory supported the idea that Theia remained largely intact, so that the moon would be largely Theia. But the sample returns from Apollo showed that it was actually only about 40% Theia, and the rest was all due to this inmixing and the shock heating of the surface of Earth and that magma ocean model, which then would have realigned all of the minerals. There would be a new isotopic signature, and that was really what the Apollo missions found, was that there was a new oxygen isotope that was specific to the surface of Earth and to the surface of the moon, meaning they would have had to have gone through the exact same, not similar, but the same shock heating event with the same angular momentum, with the same velocity. It couldn't have been just that they went through a similar process in their formation. It had to have been the same impact event that created the surface of both. We can also see that looking at the rotation of the moon and looking at its magnetic signature to support this idea of that mixing and that magma ocean model, that the moon would have to have a core that is only about 25% of the moon. And that's what all of the signatures really look like. But some of the questions remain, such as, would an impact like this have really only created one moon? And if we had this impact that created a moon that's a sixth the size of Earth, which is pretty significant, why wouldn't Venus have a moon? It's a similar density, tilted to a similar angle, located in a similar region in the solar system, and also survived major impacts. And we see that, maybe even larger impacts, because Venus rotates backwards. It was hit hard enough to actually rotate backwards. We see Mercury had its crust and its mantle completely blown away. So we see all of these signatures in the inner solar system, and Venus is the only other body besides Mercury that doesn't have a moon at all, and it should. And one of the other questions that has come up and scientists have looked at in the last 2 years is that there's a very good possibility that two moons were actually formed, that a second smaller moon, only about 1,000 kilometers, was formed in a gravitationally stable orbit just past the moon, and the sun's energy and some solar wind particles would have pushed that moon into our moon and slowly pancaked it into the backside. And if you were to look at images of the far side of the moon and the near side of the moon, you could see that they're very different. The crust is much thicker on the far side. So originally having two moons and that slow compressing of the two would explain that. And we know that these impacts have happened because we see these scars all over the solar system. And we know that due to the amount of scars that we see and the evidence of these impacts, that the early solar system would have had a lot more material. So it's likely that we will find lots more planets, many more asteroids, more comets way into the Oort cloud, because Jupiter's gravity would have done one of two things. It would have either thrown things into the inner solar system, where they would have then collided with the sun, or it would have ejected them way outside the system, where they would be way back here beyond the orbit of Pluto. And way back here, extending another 5 light years, is where we see most comets. This is where 90% of all comets are, and we're likely to find 5 to 10 more planets out there. So the inner solar system still has a lot of activity. We still see evidence of impacts. We still find meteorites, but we have only about 5 to 10% of that early material. So each of these blue lines represents the orbit of an existing near-Earth asteroid. So these are all items that are larger than 10 meters, 10 to 100 meters. So some of them are as much as a kilometer. And these are all just the orbits that have been tracked. And it is tough to track asteroids because they have an extremely low albedo. If it is an orbiting iron body, iron is very dark. Well, space is dark too. So they're extremely tough to see. And it is generally college students, grad students, and amateur astronomers that track these. So we can see one here that goes inside the orbit of Mars. There we see Earth, this tiny little dot, and it is tough to even see against the background of blue orbits. So here's showing that same scenario again. So moving on to lunar surface features. We can really break down the surface of the moon into two distinct features, the mare or maria and the highlands. So highlands are generally higher, they are saturated with craters, they are lighter material, they are older, and the maria are these dark, smooth plains where you had cracking of the crust and magma that came through. So maria are basins that are flooded with magma. So just looking at this image of the moon, we can see areas of mare. Mare would be singular for maria, and we can see areas of highlands. And one thing that is interesting is that maria is named for sea, because early astronomers, and not so long ago, like 19th century, assumed that these low-lying areas were ocean basins. Us being a larger gravitational body, Earth must have then stolen the water from the moon and left these empty ocean basins, because they could see topographically that these areas were lower lying, they were smooth. It was what they assumed that Earth's ocean basins looked like. They assumed they were these desert-like flat plains. We know that there are actually huge mountains underwater. The hugest mountain range on the planet is under the ocean, wraps all the way around the planet. But they assumed that this was what an ocean basin looked like. So they called these seas. So there's numerous plains that are named after, like the Sea of Tranquility, Mare Tranquillium. So you'll see a lot of those names on the map. So some general features of each. Highlands are lighter colored, they're much higher, and they are comprised of the moon's crust, whereas Maria is much younger, it is darker, not significantly younger, but these were created during the period of bombardment for 3.8 billion years ago, whereas the highlands are more like 4 to 4.5 billion years ago, because remember the moon formed 200 million years into Earth's history. So Maria was formed when the moon was still cooling. There would have been more of a molten subsurface, so larger impacts were able to crack that crust and magma to flow through. So the reason that it's darker is because this is comprised of a higher density material that flowed through the crust. So Mare is essentially mantle material. Highlands are the crust. Mare is older, smoother, and darker. Mare is younger, smoother, and darker. Highlands are older, lighter, and higher. And we can see that the Mare and the existence of the Mare indicates that early solar system activity around 4 billion years ago steeply dropped off. So we had a period of heavy bombardment and then it ended. So here we can see those differences between the highlands, which are heavily cratered terrain. They are much lighter. And you can see that contrasting with the smooth maria. So when those impactors happened and you had a basin that was flooded with magma, it obliterated all of these older craters. So it covered up the areas that were older and filled it with new material. And that is actually a way of relatively dating some planetary surfaces. So even if we didn't know an exact age of something, we could tell that this area would be younger than this. And we could tell that this impact in this basin is younger than this, that this impact in that lava flow had to have preceded these impacts right here. So relative dating, not absolute dating. So here we can see some images of the highlands and the saturation of craters. Here if you see the boundary between daytime and nighttime, that's called the terminator, and that's actually the best place to view craters because you can really see the shadows. We'll talk about impacts later on, but you can see some of the features of the craters. You can see how there's a central peak. You can see how there is crustal uplift. And surrounding some of the craters, you can see what looks like some smaller craters. Sometimes these can be secondary impacts from this material that was ejected up into space and then was not accelerated to escape velocity, so it crashed back into the body. So the impacts can serve as a relative dating technique. So if we know that areas have lots and lots and lots of craters, those areas have to be significantly older. That terrain had to have survived most of solar system history and carried with it all of the impact signatures of it. Whereas the maria being very smooth and low-lying, you can tell that that area has to be younger because it doesn't have so many craters. So areas that have lots and lots of craters are generally older, and this is not just used for the moon, this is also used for Mars, this is used for Mercury, so trying to date specific terrains, and the only way we have to do that is through crater counting. So when I was looking at my thesis and I was looking at asteroid Vesta, that is how we were able to tell which areas were younger, which are older, and that's important because the only erosion that these bodies go through is due to impacts, and the impacts can melt the material at the surface, which can change the composition of the minerals, which can then change the process and the albedo, and it's a whole cycle of feedback that happens. So, so being able to tell which areas are older is really important, and the only way we have to do that is the relative abundance of craters. So we can see highland rocks have so much more, so they're generally 3.8 to 4 billion years old. The mare, which would be basaltic is like what Earth magma is, would be about 3.1 to 3.8 billion years old. So we can see that there is this sharp drop-off in cratering. So we can see that the highlands would have formed back here, and through time, the cratering would have dropped off, and here would have been where the mare formed. So once you get past all of the highlands and the maria, the entire moon is covered in a fine dust called regolith. This is similar to terrestrial soil, except that regolith is not altered by any sort of oxygen or water. The only erosion on the moon is due to impacts. So all regolith are these sharp little glass fragments. So they're essentially volcanic rock that has been mechanically eroded, just ground smaller and smaller and smaller due to impacts. So it's not very smooth dust. This is, under a microscope, these are very sharp edges. And the reason is there's no surface water there. So rocks on Earth have surface processes like wind and water and motion that can erode them away. Well, there's none of those things on the moon, so all of these edges are very, very rough. So if you were to breathe it in, it would literally tear up your esophagus. This is not just like dust. It would be like breathing in glass shards. So regolith is incredibly fine, 1 centimeter or less. And this is essentially a powder that's overlying the lower bedrock. And this is all igneous rocks. So if you think about magma or lava on Earth, that is all igneous rock. There is no process to create sedimentary rocks or metamorphic rocks like we have on Earth. It is all igneous. And we see this in other planetary bodies. It is all igneous. We are the only planet we know of that has metamorphic. So there's a link to a video. So here we can see some of the different types of regolith and lunar maria, so you can really see here how fragmented it is and how sharp it looks. There are some volcanic glass beads, but remember that there isn't volcanoes the way we think about volcanoes on the moon. That magma was there due to crustal cracking and flowing of magma, not volcanic. And this is a real problem for actually sending people to the moon. So this is a Soviet cosmonaut, is what they call them in the Soviet Union. And you can see that his spacesuit, which was once white, is now very much not white. So you can see that it is very, very, very dirty. And this was a major problem because when astronauts were first coming back from the Apollo missions and the Soviet Luna missions, they were finding that even being out for a couple hours on the moon was completely disintegrating their spacesuits. So, for example, this is some of the spacesuit fabric from NASA, and just from being out here, you can see how dirty it got and how much it deteriorated. So where I got my my master's at University of North Dakota, they, MIT, and one other university that I can't remember the name of, they're designing the next NASA spacesuits. And it has to be totally resistant to this regolith, and this was not something that NASA accounted for at all. And under a microscope, you can see how it's just completely deteriorated the material. The spacesuits were complete junk. So just an overview of some of the moon missions. These were some of the very first manned missions. The last manned mission was in 1972. As far as unmanned missions, we started sending orbiters, us and the Soviets, in 58. We started sending impactors to impact the surface and analyze the spectral signature of what was ejected out in 1958. And we started flybys in 58, and we're still doing those. So anytime we send anything to the outer solar system, we do a flyby. We slingshot around the Earth to gain acceleration and velocity. We then slingshot around the moon. So every time just getting a greater understanding and imagery of our closest neighbor. So in the future, some of the major players in the space game are going to be Russia, China, and Japan. You can see us, we're down at the bottom with Europe. China has been for a couple years now unsuccessfully sending unmanned probes. They are trying to establish a lunar base. They've had a plan to establish a lunar colony by 2025. However, they can't seem to get an unmanned lander to land there successfully. However, China has a ton of money that they are putting into their space program, as is India. India has grown a really robust space industry in just the last decade. But China has a very quickly growing launch program. They're launching as many as 3 rockets a day, and it is incredibly secretive. So it's very tough to actually find out what China is doing. They've had a lot of rocket failures, and they're just not releasing a lot of that info. So they're very quickly pushing to try and get further their space technology. So that is it, guys. I know this was a long one, but it was combining 2 sections. Have a great night.